In this video, we're going to look at the integrating factor type for first order differential equations. So this occurs when we don't have a function and its derivative where y is. So we need to coerce it to make it look like that, and we can do that by using the integrating factor. So what we need to do is say that whatever the coefficient in front of y is, in our case it's -4, we're going to use that in our integrating factor. But it's important to notice that in general we would want it in the form of dy by dx minus something in front of y equals a function. And we're going to use this coefficient in front of y for this integrating factor. So the integrating factor, which I'm going to abbreviate as IF, is always e an integral, and whatever the coefficient of y is, we're going to put it here. So -4 and dx. So that's going to be the same as e to the power -4x. So what we do now is we multiply throughout by the integrating factor. So multiply throughout by the integrating factor, like so. So I'm going to use a pink pen for this. So it's e to the power -4x followed by dy by dx -4, and then we multiply by the integrating factor, e to the power -4x, and then here we've got e to the power of x multiplied by e to the power -4x. So simplifying that down, we're going to get the following. We're going to get e to the power -4x dy by dx -4 e to the power -4x. Now for the laws of indices, this will give me e to the power -3x. Now we have it, we've got a function which is e to the power -4x, and we've got the value in front of y, put the y in there, is the derivative of e to the power -4x, namely -4 e to the power -4x. So now what we can do is do what we did before. So say d by dx, write down the function, e to the power -4x, then we've got a y, and that's equal to e to the power -3x. So I'm going to integrate both sides. So I'm just going to write this step in like this so you can see how the working out follows from one another, and for clarity as well. So we get that is equal to the integral of e to the power -3x dx. So that will just give me e to the power -4x y. This will be standard integration, -1/3 e to the power -3x plus the arbitrary constant. So let's divide everything by e to the power -4x, like so, and we end up with the following. We get y is equal to -1/3 e to the power -3x divided by, so I'm going to write that step in, -3x minus -4x plus c over e to the power -4x. So I'm just doing that so you can see how I get my final answer. So I know for some people it'll be intuitive, but I'm just trying to show all my steps of working out here. So -1/3 e to the power -3x plus 4x plus c over e to the power -4x, and therefore our final solution would be y equals to -1/3 e to the power of x plus c over e to the power of -4x. Well, we can also write it in another form, or we could write that as minus a third e to the x plus c, and bring e to the minus 4x up, so we get e to the power of 4x, like so. Here's a question for you to try. You can pause the video, and when you're done, I will go through my work solution. Okay, welcome back. So again, we have a question type where we don't have a function as derivative, but it's in the correct form, dy by dx plus something in front of y, and is equal to a function. So we're going to use the integrating factor here. So I'm going to say the integrating factor if is e to the integral of the coefficient in front of y, which is 2. So it's 2 dx, and that will give me e to the power 2x. So we're going to multiply throughout by the integrating factor, and again following our same principle from before, so it will be e to the power 2x dy by dx. I'm just writing it in pink so it's vivid for you, so you can see what's being multiplied. So plus 2y is times e to the power 2x, and then we're just for clarity just going to write this down, e to the power of x times e to the power of 2x. So we end up with e to the power of 2x dy by dx plus 2e to the 2x y equals to e to the power 3x. So now we have it. We have a function e to the power 2x, and its derivative is in front of y, 2 e to the 2x. So now we can go ahead and do what we normally do. So it's dx e to the 2x, and put a y here, e to the power of 3x. So we're going to integrate both sides, like so. And e to the power of 3x dx. And then we end up with the following: e to the power of 2x y equals e to the power of 3x over 3 plus the arbitrary constant. So now we're going to divide everything by e to the power of 2x. So we're going to say it's y is equal to a third. Now e to the power of 3x divided by e to the power of 2x is just simply e to the power of x plus c over e to the power of 2x, like so. And that's our solution. Now I wanted to go through this particular example because initially this example looks a bit deceptive. It appears apparently that we've got a function that's derivative, but we truly don't, because we know that the differentiation of cosine of x is minus sine of x, and the minus sign is not here. So what we need to do is use the integrating factor type. But first of all, we need to make it look like dy by dx plus a function and is equal to another function. So namely dy by dx plus a function times y equals to a function. So what we're going to do is divide everything by cosine of x, first of all, in our equation. And if we were to do that, cosine of x divided by cosine of x is simply dy by dx plus 2y, and I'm going to write this in full so we can see it, sine x divided by cosine of x, which we know is going to give us tan of x, equals to cosine the power 4 of x divided by cosine of x. So what happens here is we now end up with dy by dx plus 2 tan of x and I'm just going to write the y here so we can see that the coefficient in front of y is 2 tan x, and that's equal to cosine to the power of 3x. So, or cos cubed x. So now we have the differential equation, the form we want. Now it doesn't appear in the function, and where the value in front of y is the derivative of that function in front of dy by dx. So we need to use the integrating factor. So we're going to say that the integrating factor is e, and the integral, I'm going to put the constant outside, 2 tan x dx. Now you should know all your integrals, so you should know that the integral of tan x is ln sec x. And I can use the laws of logs here to give me ln sec x squared to improve the clarity of that. So that's going to just simply give me sec squared x, because e and ln will cancel out. So now I'm going to multiply throughout by the integrating factor. So multiply throughout by the integrating factor, and we're just going to show that multiplication in pink. So it's going to be sec squared x times dy by dx plus 2 tan x, so plus 2 tan x, then we've got sec squared x, and then we have a y, and that is equal to cos cubed x multiplied by sec squared x. So what we can do here is write this as sec squared x dy by dx plus 2 sec squared x tan x y equals, now I'm just going to do this for completeness and write cos cubed x times 1 over cos squared x. So I'm just showing all the steps here so it's clear why I'm doing that. So what we end up with is sec squared x dy by dx plus 2 sec squared x tan x y, and that's equal to cosine of x. So now the question we need to ask ourselves is, well, we need a function and its derivative. So if you're clear in terms of differentiation, I'm going to show this step for clarity. You would see that the derivative is actually here, but for some people you might be asking, well, how? Well, so let's write the function down. Y equals to sec squared x. Well, what would happen if I differentiate that function? That will give me dy by dx. We bring the 2 down, so it's 2 sec x, and the power goes down to 1, and we need to multiply it by the differentiation of sec x from the chain rule in differentiation. So that's going to be 2 sec x, and I'm going to write the differentiation in pink here. So that gives me the differentiation of sec x is sec x tan x. And now if we were to simplify that, it will give me the following. It will give me 2 sec squared x tan x. Now that's exactly what we have in front of the coefficient of y. So now we do have the differentiation of sec squared x there in front of y. So now we can do what we always do. So we're going to write d by dx, therefore d by dx of sec squared x multiplied by y is equal to cos x. Now we're going to integrate both sides. So we're going to say the following: d by dx sec squared x y equals the integral of cosine x dx. Well, that will give me sec squared x y. Well, the integration of cosine of x is sine x, so sine x plus the arbitrary constant. So now we're going to divide throughout by sec squared x. So for clarity, I'm just going to write this as follows. So I'm going to write it as sine x divided by 1 over cos squared x plus c over 1 over cos squared x. So because we're dividing two fractions, we could do the following. We could write this as cos squared x times the following, sine x plus c. Then part B says, find a particular solution which satisfies the condition that y equals 2 when x equals 0. So we need to substitute these boundary conditions into our equation. So we're going to say, for part B here, when y equals to 2 and x equals 0, we get the following. 2 equals cos of 0. I'm going to put this squared, that's what the cos squared x is, multiplied by sine of 0 plus c. Well, we should know that cos 0 is 1, so we get 1 squared, which is 1. I'm going to write that in full. 0 plus c. So 2 equals to 1 times c, so 2 equals to c. So we now know that c is 2, so we can say therefore y equals to cos squared x multiplied by sine x plus 2 is the particular solution that we're looking for.